Hello and welcome. In our video today we are going to talk a little bit about higher derivatives and a relationship that has to finding something called an antiderivative. So we've been thinking about the derivative as an operator. d dx is this operator that takes a function of x and it generates from that a new function which we call f prime, the derivative of f of x. So d dx of f of x is the f prime function. That's the derivative. Now, f prime of x itself is a new function, so we could apply d dx a second time to find the derivative of f prime of x. d dx of f prime of x is a new function, which we read f double prime of x, or the second derivative of f of x. And in fact, this keeps going. Now that f double prime of x is a function, we can do it again. We can take the derivative of f double prime of x, and we get f triple prime of x, f prime prime prime, the third derivative. And this process would go on forever. Once we get a derivative, we could find the next derivative. So writing a little tick mark, an apostrophe, gets hard to keep track of. And so once we start getting into high derivatives, we usually don't write a number like tick, 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 tick. We instead put in parentheses the number of derivatives we're finding. So f parentheses 2 of x is the second derivative, and f parentheses 3 of x is the third derivative. F parentheses 4 of x is the fourth derivative. So these are higher order derivatives. So for example, if I had this function, f of x is the x to the fourth minus 2x cubed plus 5x minus 1, and I want to find the first three derivatives, then I will calculate a new function, f prime of x, the first derivative. I'm going to take the derivative of f of x, and so I'll just think on each term, right? X to the fourth has a derivative from the power rule of 4 times x cubed. And negative 2x cubed, its derivative will be negative 2 times the derivative of x cubed. So our next term is negative 2 times 3x squared. And then I get to the next term, 5x, that's linear. Its derivative is 5. And minus 1 has a derivative of 0. A derivative of a constant is 0. So my first derivative is 4x cubed minus 6x squared plus 5. And that's a new function. It's a polynomial. I can take a derivative of a polynomial. F second derivative, f double prime, is what I get when I take a derivative of the f prime function. So this time I'm focusing on f prime as a function, and I'll do again the derivative of each term. 4x cubed has a derivative 4 times 3x squared. 6x squared has a derivative, so we'll write minus 6, derivative of x squared is 2x. And finally, plus 5, its derivative is 0. So my second derivative is 12x squared minus 12x. That's the second derivative. And to find the third derivative, because f double prime is a function, I can say, well, let's take a derivative, d dx of f double prime. This is my second derivative. And its derivative is the derivative of 12x squared. That's 12 times 2x. 12 times 2x minus the derivative of 12x, and that's minus 12. And so I get 24x minus 12. That's the third derivative. And I could keep going. Here I only asked for the first three, but the next derivative would be 24. And the next derivative, well, let's write it out. Why stop, right? So 4 ticks is a little too much for me. I'll say the fourth derivative of x is the derivative of 24x minus 12. That's 24 plus 0. F fourth derivative is a constant, the fifth derivative is the derivative of a constant. That will be 0, and that's a constant. And so the sixth derivative is 0, and that's a constant. And so every derivative after this is just going to be 0. Those are higher order derivatives. Okay, so with this idea that going from a function and d dx finds a new function, right? If I start with f of x, I find its derivative. That's a new function. I take its derivative, I get a new function. I take its derivative, I get a new function. What about going backwards? Is there a function so that when you take its derivative, you land on f of x? If so, that function that shows up before in, I think of this as like a ladder of functions, the function before is called an antiderivative of f of x. So for example, in our previous work, we saw that 24x minus 12, let's go use that. We know that d dx of, what was our original function? 12x squared minus 12x. 12x squared minus 12x is 24x minus 12. That means that this function, f of x equals 12x squared minus 12x, is an antiderivative of 24x minus 12. This would be my f of x function. This is the antiderivative because when you take a derivative of it, you get the 24x minus 12. And what we want to do is we want to think about, well, how could we, if we didn't know it in advance, how would we go from this function back to the original? Okay? Now, we've realized that when I take a derivative of a constant, we get 0. So if you can find one antiderivative, adding any constant is going to be yet another antiderivative. So these aren't unique. There's going to be families of antiderivatives. So the most common tool that we're going to need to understand for finding antiderivatives is figuring out how to undo that power rule. A derivative of, so for example, if I take a derivative of x cubed, I get 3x squared. And so notice what happened. The power went down. If I want to find an antiderivative and I'm working with x squared, the antiderivative somehow has to go back to a power x cubed. And so this process, this reverse power rule, is going to walk through this process of recognizing how to do that. So notice what we did. We identified a power, n equals 3. And we use that power as the constant, which is multiplying by x, which has a power that went down by 1. And so if I want to do an antiderivative, I need to reverse those steps. And because I need to reverse the steps, I'm going to have to undo it by going in the reverse order. So I'm going to identify a power. Let's do an example here. If my function f of x is, for example, x to the 4th, right now, n equals 4. Okay? The antiderivative needs to work with a new power, n plus 1, and that's 5. Okay, so my antiderivative is going to be an x to the 5th power kind of function. But notice that in a derivative, I multiply by this larger power. And so the reverse of that is I need to divide by that power. So my antiderivative is 1/5 of x to the 5th. And let's check what happens. If I take a derivative of 1/5 x to the 5th, then at the moment, the 1/5 is just a constant multiple. So it stays, it sticks around. And then I'm going to multiply by the derivative of x to the fifth. That's 5x to the fourth. And the magic of this reverse process is the 1/5 times the 5 cancels, and I get back to x to the fourth. And so that's why if I take a derivative d dx of 1/5 x to the fifth, I get x to the fourth. And that means 1/5 x to the fifth, 1/5 x to the fifth is not the, there's multiple, is an antiderivative. It is an antiderivative of f of x equals x to the fourth. And the official notation for finding antiderivatives involves integrals, and we don't really want to understand that finding an integral process. So I'm going to write it like inverse functions. If you take an antiderivative is the inverse of a derivative of x to the fourth, I get 1/5 x to the fifth. And adding any constant that you have is also going to be an antiderivative. Okay, so let's walk through a couple more examples and see if we can think through them. We're just going to use this reverse power rule. In this example, n equals 3. And so an antiderivative, I need to up the power. The antiderivative is the power goes up, and where the derivative multiplies, I would, instead of multiplying by 4, I divide by 4 to undo it. This is an antiderivative. If I want another antiderivative, I might add 2. That's an antiderivative. And the reason is because, I should say f of x is an antiderivative because when you take a derivative of 1/4 x to the fourth plus 2, you get 1/4 times 4x cubed plus 0, and the 1/4 times 4 cancels, I get x cubed. The antiderivative is the function that when you take its derivative, you get x cubed. Now let's see, little g of x is x to the fifth, an antiderivative. The power this time is 5. My power of the antiderivative had to go up to 6, and I divide by 6. Okay? When I see a square root, I can't work with that. I'm going to use a power. So x is 1/2. My power is 1/2. The power that's increased is actually 3/2. And so an antiderivative, I'm going to have x to the 3/2. And I need to divide by 3/2. But instead of dividing by 3/2, it's the reciprocal. I multiply by 2/3. This is an antiderivative. We check our work by taking a derivative of what we thought was an antiderivative. I get 2/3 times, all right, the derivative of x to the 3/2 is 3/2 x, and the power drops by 1 to 1/2. And sure enough, the 2's and the 3's cancel, and I get x to the 1/2. So yeah, we did find an antiderivative. And if you needed a different antiderivative, you'd add some constant. Okay, derivatives allow me to focus on one term of a time when I have constant multiples and addition. So because I can focus on one term at a time, antiderivatives will work the same way. I keep the constant multiples, and I work with the powers of each one at a time. So if I saw this polynomial and I wanted to find an antiderivative, the antiderivative that I start with, and I could add a constant later, is going to be an antiderivative. I'm going to undo a derivative, so d dx inverse of 2x to the fifth minus 3x cubed plus 4 is going to, I'm going to focus on one term at a time, constant multiple, and then an antiderivative of x to the fifth, which we know is 1/6 x to the sixth. And then minus 3x cubed. Okay, that's a constant multiple of minus 3. X cubed, that's a power. The new power is x to the fourth times 1/4 plus 4. What has a derivative of 4? It doesn't look like a power rule, but we know that linear functions have derivatives of constants. Linear functions are the functions that have constant derivatives. So what do I get? I get 2 times a sixth, that's 1/3, x to the sixth, minus 3 times 1/4, that's a fraction 3/4, x to the fourth, plus 4x. This is an antiderivative, and so is any constant added to that. So my antiderivatives that I might consider are polynomials. The power had to go up by 1, so x to the fifth goes to x to the sixth, x cubed, its antiderivative has x to the fourth, and the constant, which you could recognize as an x to the 0 term, goes to an x to the first term. Okay? And this is how I find antiderivatives.